Okay, so this is example number 2, our last example for load analysis. In this example, is even more complete example on how we will do actually a real machine. So let's start with it. I borrowed this example from Hamrock's machine design textbook. So you can see that here we are working with a machine that actually manufactures rolled flat sheets. It looks like a very complex machinery, and we want to analyze one of these parts right there. Okay, so after just breaking all this apart and just really understanding what's going on in the problem, we can simplify the problem with the following numbers. This F is the resultant between these two. So you can see that many times, and that's what we do, we take a very complex problem and we simplify to one dimension if it's possible. Um, so in this particular case, we were able to do it, and this is the problem that we have in hand. The next thing we want to do is we need to find our reaction loads, and we need to find your F. So that's what we're going to do next. The total amount of force, this is pulling up there, this is pulling up there. So the total amount of force that's really pulling completely up is 180 plus 540. That will be 720 pounds here. And to find the reaction loads, I take a summation in X, in Y, and a summation about this point right here. I take a moment and I'm able to find my RA, my RBs. Okay, I'm guessing this is something that you should know, and so we will continue. I just want to clarify one or two things before we move on, actually. And one of the things I like to emphasize to the students is that when we are solving these problems, many times we are using summation of force is equal to 0. We are kind of being sloppy here. Really, the correct version of the Newton's second law is summation of m over a, which is not correct either. The real version says Newton's second law states that summation of m of the forces is equal to rate change of momentum. Okay, this is correct. So we expand this, rate change of mass respect to time times velocity times mass times rate change of time speed versus time. And well, you can see that in the case that you're working a rocket design where your mass is, you're burning fuel at a very high rate, this term is not equal to 0. Most of the problems that we design in machine design, if it's not aerospace related mainly, we can assume that this is a very slowly varying function. By slowly varying, I mean the following. I mean that you can have a problem that's respect to time, and you got the mass, and the mass may be changing, right? But as I move along the time, if I take a small delta t, that delta t states that my delta m here, my delta m is almost equal to 0, or is very small. Or another way to write this is way smaller than 0. In such a case, I can say this is equal to 0. This is called a slowly varying mass. Okay, and this is also true. This will also be true if I did the same thing for my velocity. If your speed is actually It's a slowly varying speed with time. I'm not saying it doesn't vary. It can go up, it can go down, it can change. But if I take a very small delta t, in that delta t, I am saying that the value of delta V is way far smaller than zero. So in other words, or maybe I should take the absolute value. In other words, what we are saying, this is almost zero. So basically, if they are slowly varying functions, only under those cases can I say and I can state that this term is zero, this term is zero, and then I can get this equal to zero. And if you realize this is your A, right? This is mass. So this is summation of forces is equal to mass times acceleration. This term is kind of sloppy. It's not complete. This is complete. And this is important to understand. It's a rate change of momentum that is true for Newton's second law. Okay, just like to make that emphasis. And the same thing is true for, so this is true only under this case. And same too is for inertia, right? This is the rate change of the inertia times omega. Okay, so I'm sorry, times rho. So this is what we are really trying to change, is the change of momentum. We can say zero, we can assume the inertia doesn't vary and the speed doesn't vary, okay? Just want to make sure that's clear for all of us. So now let's move on to solving the example that we have in hand. The example that we are discussing can be basically after putting all the values, this is the equation that we have. And if we talk about this equation now, you can say, I may ask you, how many times, so for this particular problem, how many different sections do we need to divide? Let's see, and you answer. How many? Correct. It will be 3. Why? Because how many discontinuities do I have? I have, this is a discontinuous. I always start with the first cut. Then I have a load discontinuity. And I have another discontinuity because of loads and also because of boundary. So in this case, I have 1, 2, 3. And this section 4 will be just for a check if you needed one. But you really have 3 section cuts. Okay, so if you move on, let's start doing our section cuts one at a time. So the very first section cut, we will do it we are doing a section cut here. Okay, so for this section cut, we're going to place our loads in the positive direction. So that would be V in this direction. It will be, this is Vy. We don't have any VZs in this problem, so it makes life a little bit easier, Nx. And I have a moment, Mz. Now, before I start, I need to figure out what my load here would be for Vy at 0 plus. To do that, I make a small cut. This cut is at x equal to 0 plus. Remember, this is 0. It's just looking from the right hand side. So I have a load 430 pounds, and my positive V is Vy in this direction. So it gives me Vy plus 430 is equal to 0. So your Vy is minus 430. Okay, so that is the value of V sub 0 that we're going to use here. Now, moving, and then I have to do the same thing. I don't need to do anything else. So the first section cut I will do is right here. And that section cut basically tells me Vy of x, section cut number 1, tells me this is equal to Vy at 0 plus minus 0 times x Py xi times xi. And we don't have any distributed load, so this goes to 0. So a section cut is equal to this. So for my V1, this is equal to minus 430 pounds. Okay, so we know what my shear is in this section, and knowing the shear in this section, now I can go ahead. I'm going to delete all this. You can always go back in your video to take notes. Now let's go find NXX. NXX doesn't have any loads. Since it doesn't have any load, even if I did apply any load, is 0. So you know that NXX at NXX at 0 plus will be 0. Okay, so that's the value that would be right there. So if I did this, is NXX of x of 1 will be NXX at 0 plus minus 0x px psi dx psi, and this is 0. So you basically end up this equal to 0. Okay. Now, if I did my moment, okay, the next thing we do is the moment, and let's delete all this again. Now, when we do the moment for the first section, we do this again. As you know, we always want to find what m sub 0 is, and you can show that that's actually equal to 0 starting in this location. So mzz of x will be mzz at 0 plus minus, if you recall our equation, is Vy of x d of x. And this is 0, so it will be 0 minus, and this is 1, 1, 1, sorry. And this was minus 430 d of x. So mzz1 of x will actually equal to 430 times x. So now we found all the loads in the first segment. Let's move on to the next one. Okay. The next segment, there are two ways to do this problem. This is the location where I'm trying to do. And the way I like to do this problem is the following. I like to say, let me go ahead and do the following. Let me go ahead and see, let me make a section cut and right at 10, okay, this is 10. So this is 10. This would be what happens at 10 plus. This is section cut number 2, NXX2. This is what happens at 10 plus. But then this side over here will be 10 minus. It's same point, it's just seen from the other side. Okay, so I want to know what my NXX2 0. On this side, if you let me just write this down first, and I'll explain this in a minute. If you realize when you are on this side of the equation, right? On this side, exactly on this side equation, this is nothing else than uh, nxx1, but evaluated at 10. This is nothing else than by1 evaluated at 10. And this is nothing else than mzz1 evaluated at 10. Make sense? Because you're evaluating going all the way up to here, and I want to know my starting point there. Okay? Given that, let's go back to our equations that we found. Okay, let's leave this over here. And the equations that we found were by1 of x was equal to minus 430. So therefore, if I replace this by 10, I will get the same value. nxx, really, I don't have any nxx in this problem. So these are all 0. Now, I do need to know mxx because I have a torque that's applied there. Is 0 in the first segment. Okay, so it's 0 there. I'm going to have a mxx. Simplify, I'm going to eliminate this. Since we don't have absolutely no axial loads, it will actually give you 0. Then you have mzz at 0. We said that was equal to 430 times x. I'm sorry, in times x. We just found that. So if I go ahead and I replace this by 10, then I will replace this by 10, and the answer you will get is 4,300 pound inches. Okay, this is the value of this. So these are the values that happen on the 10 minus, 10 minus, 10 minus, 10 minus. These are the values seen from the left-hand side, not the right-hand side. These are the values I need to find now in order to do all my analysis. Okay. So with that said and done, let's go ahead and simplify this a little bit so we can make it clear. So my Vy was minus 430. Don't need to flip it, just leave it like that for now. Mxx was 0, so I don't have any Mxx, that's a 0. This one, in my positive sense, is 4,300. So all I need to do now is I need to go ahead and find these guys, right? Doing a free body diagram, you basically find that this is going to be, if you realize this is, let's do it, minus 430. The arrow is going downwards. The value is negative. And this is going downwards. This is 0. So Vy is actually equal to 70 pounds. Vy2 is constant. At this point, it's going to be just a value. So, and then finding your torque, or torque at 2, remember when I say at 2, I'm talking about the values at 10 plus. Okay, this is not value for the whole thing. We need to use our equations. So the torque tells me this is 0, minus 6, 0, and plus mxx is equal to 0, 2. So mxx2 will be 2,160 pound inches. Remember, this is positive. So we found that as well. And delete this. To find your MZZ, MZZ at 2 will be nothing else than 4,000, 3,000, 4,300, and you can show that to yourself. Okay, so now we found these values. The next thing that we want to do is, we found all these values, so we know that this is equal to 70. We know that this is equal to 4300. We know that this is equal to 2160 positive. So let's come, we did all this just to find the loads here. We did all this just to find these loads. Okay, that's what we did. Now we need to use our equations. Remember, V2 of x will be V2 at 10 plus minus, again, 10 to x py dx, and we don't have this. So this will equal to 70 positive. We do the same thing for MZZ2. MZZ2 will be MZZ2 evaluated at 10 plus minus 10 times x vy2 d of x. And when you evaluate all this, you find, going to jump some steps here, this will give you minus 70 plus 5,000. Okay, you can show that this is the value you will get. And then MXX2 would be MXX2 at 10 plus minus 10 times x, your distributed moments, if we had any, and we don't. So this is basically 2,160 pound-inches. Okay, so this is your next section. So now we move on to the third section, and we do exactly the same thing, but now I need to repeat the same process I did before. Need to do the same process as I did before, but I need to find what are the loads, the moments here and here. I need to find what the loads are here at 20 minus. This is the location of 20, and 20 plus is what I'm really interested in. But I need to be very systematic about this in order to find my moments and everything. Okay, so we have done this several times. We only did this once. I will let you go through the process, and I will let you be able to show that the loads that we are looking for are following. The loads in MXX2 are 2160. Your shear in 3, I'm sorry, of x will be 720, and then your moment in 3 of x will be minus 720x plus 18,000. Okay, so now that we have our loads, now that we have all these values, the next thing we want to do is, we got the loads, we want to plot them. Okay, so we will use MATLAB. So let me just show you how that is done in MATLAB. Okay, let's go back to MATLAB. And so I'm going to open in your MATLAB, it says load diagrams. So by the way, this is in my, this is example 5.4. These notes are posted under Machine Design book, page 343. You can take a look at it. The full example is there. So if I did this problem, now you need to divide this into 4 elements. Why? Let's go back. Remember, how many do you have? 1, 0. The next one is 10. Let's save this as example 2. Okay. And then the next one is 20. The last one is 25. And you can see where these come from, right? So if I move these, this node is 0. This will be 10. This will be 20 because we are starting from here. This is 25. This is where it comes from. So I'm going to keep 100 data points in this example. You can put as many data points you want. Okay, doesn't matter. It's just going to take more time to do your plots. So now I need to, since I'm doing one plot, remember this is only one beam. I'm dividing this beam in 3 parts, but you want to do one plot. That's why in MATLAB you have to put x1, x2, x3 all together. Don't forget to put this transposed, otherwise you will have errors. Okay, so in our load analysis, I did not have any NXX, so that's why I multiply 0 times 1s. And then again, these are all my loads for N1, 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 N2, and 3. Okay, so now my loads, let me show you what my loads are. The first load was, if I'm not mistaken, let me find it very quick. It was minus 430. You multiply by that, by 1s. 70, you multiply by that. I don't need to put a dot. You can, because I'm multiplying by x's. And then my last one was 720. Okay, so and my moment in x, a moment in z, my first value was 430 x1. Second value was just give me a sec, was minus 70 plus 5,000. Note that for my second segment, I'm using x2. Okay, don't use x1, you're going to get an error. And then your last segment is minus 720 times x multiplied by 18,000. Okay, those are the equations that we got. And my torque, the first was 0, and this was 266. Okay,